In this example problem, we are on a planet far, far away, so dramatic, and an astronaut picks up a rock. This rock has a mass of 5 kilograms, and on this particular planet, its weight is 40 newtons. If the astronaut exerts an upward force of 46.2 newtons on the rock, what is its acceleration? So just like any Newton's second law problem, you need to start by drawing a picture, which I've already got started at the bottom here. And then on this picture, we need to start constructing our free body diagram, which I've outlined all the steps in the previous notes that shows you how to draw a free body diagram. So let's go through those steps step by step. So step number 1 says sketch all the forces. Okay, so let's look at this problem carefully. The rock has a mass of 5 kilograms, and on this particular planet, its weight is 40 newtons. So there's our first force. It says the weight is 40 newtons. Now remember that the weight is caused by the force of gravity. Now that's important, okay, because a force is a vector. And we're going to assume that on this planet, okay, the force of gravity is acting straight down. So just like on Earth, it's acting straight down. So when I draw my weight force, which is the force of gravity, it should be straight down as well. Okay, so straight down, and we'll label that as W. And we'll say that's equal to, so that's my weight, that's going to be equal to 40.0 newtons. Now, step 1 says identify and sketch all the forces acting on the object. Okay, so we're also told that the astronaut exerts an upward force of 46.2 newtons on the rock. Okay, so there's a second force here that we need to draw. And we're going to assume that it's directly upward. It's straight up, this force that the astronaut is applying. So the astronaut is applying a force straight up. We'll call that, say, F sub A. So the force from the astronaut, which is equal to 46.2 newtons straight up. Okay, now step number 2 says isolate the object of interest. Okay, so what that means is in this problem we're interested in the acceleration of the rock. So we want to isolate the rock by replacing the object with a point particle of the same mass. So what that means is instead of having this big red blob, which is the rock, I'm just going to represent this rock by a single point. So off to the right, I'm just going to draw a single point. And that point should have the same mass as the rock. So that point we're saying its mass is equal to 5.00 kilograms. Okay, so that point has the same mass as this rock. And step number 2 also says apply each of the forces acting on the object from that point. Okay, so in this case, I've got the force from the astronaut and the weight, all of which need to be acting from that point. So I'm going to redraw these forces from that point. Draw it straight down. This is the weight, okay, equal to 40 newtons. And then I have my other vector going straight up. That's the force of the astronaut, and that is 46.2 newtons. Okay? Now, step number 3 says choose a convenient coordinate system for this problem. So we need to choose a coordinate system that aligns with one or more of the forces acting on the object. Now, because this is the first problem of this homework set, we're starting off really simple. In this problem, we only have 2 forces here, and they're both acting in the y direction. So we want to set up our coordinate system to where one of our axes, so either the y-axis or the x-axis, is parallel or perfectly lined up with both of these forces. So since we're starting off simple, it just makes sense to say that straight up, so straight up is going to be our positive y, and straight right, okay, straight to the right, directly right, is positive x. So that's the coordinate system that we're going to use to solve this problem. Now, step number 4 says we need to break the forces into components. Well, in this problem, we've already got their components. Since the force applied by the astronaut and the weight of the rock are parallel to the y-axis, we know that the force applied to the restaurant is the y component. So there is no x component to the force that the astronaut applies, and there's no x component for the weight because they're both in the y direction. So what we can say is that the force applied by the astronaut is equal to the force of the astronaut in the y direction, and that's going to be equal to 46.2 newtons. And we also know that the weight, okay, so the weight is also equal to the y component of the weight, according to the coordinate system that we set up. So the y component of the weight is 40.0 newtons. And just for clarity, we can say that the force of the astronaut in the x direction is equal to the weight in the x direction, which are both equal to 0. Okay, but the only reason that they're both equal to 0 is because the two forces are parallel to the y-axis. Now, step number 5 says we need to apply Newton's second law to each coordinate direction. Okay, now what does that mean? Well, that means that you need to go to your equations of motion summary and look at Newton's second law and grab the equation that's most appropriate for this case. So since the forces in this case that we're dealing with are only in the y direction, it only makes sense to use the y component equation, which I have written on the second slide. So we have the sum of all the forces in the y direction is equal to the mass times the acceleration in the y direction. Okay, so let's just clarify a few things, though. We have the force of the astronaut, so the force of the astronaut in the y direction is equal to the 46.2 newtons. Now, you can see, according to the coordinate system that we set up, okay, the force of the astronaut is pointing straight up, so we know that its value should be positive. So we're going to leave that value as positive, which it is right now. But, okay, now that we've set up our coordinate system, we know that anything acting downward is in the negative y direction. So when I start summing these forces together, I have to remember that the y component of the weight is actually negative 40 newtons, so negative 40.0 newtons, because it's acting downward. Okay, so those are all the forces acting on this rock. Now, remember, this sign says that you just add up all the forces in that direction. So in this case, it's going to be 46.2 plus negative 40. So let's write that out. We've got 46.2 newtons, okay, plus, so we're summing the negative 40.0 newtons, which is equal to 46.2 newtons, okay, minus 40.0 newtons, which of course is equal to just 6.2 newtons positive. Now, don't forget, okay, this is just the left-hand side of our equation. So the sum of all the forces is 6.2 newtons. So 6.2 newtons is equal to the mass times the acceleration in the y direction. So I take the sum of those, so 6.2 newtons is equal to, okay, now the mass here, in this case, we know what the mass of this rock is. It's 5 kilograms. So the mass of the rock is equal to 5 kilograms. And now we just plug that into our equation for the mass. So right where the mass is, we plug in 5 kilograms, and I get 5.00 kilograms. And I'll just put that in parentheses to make it a little clearer, times a sub y. Okay? Now, remember, the goal of this is to solve for the acceleration. We want to know what the acceleration of the rock is when these two forces are acting on it. So at this point, it's really straightforward. We just divide both sides by 5 kilograms. So 5.0 kilograms. Divide the other side by 5.00 kilograms. Of course, the 5's on the right-hand side cancel out, and we're left with a y is equal to, okay, so just typing this into your calculator, 6.2 divided by 5 gives you 1.24, so 1.24, and that's going to be meters per second squared, and that's our final answer. Okay, so if you have any questions about this, just let me know, but I do want to make one more final point. Notice that the acceleration is positive. Okay, now what this means is that this rock is accelerating upward at 1.24 meters per second squared. Now that would make sense if you just think about it conceptually. The astronaut is exerting a greater force than the weight. So since the force of the astronaut is greater, we would expect this rock to be moving upward. So it makes perfect sense that our acceleration in the y direction is positive. Alright, hope you enjoyed this problem. If you have any questions, just let me know.